Hello, this is Jacob. I'm doing exam 3 SA1 questions. And yeah, let's get started. So first part is to describe the action potentials in cardiac ventricular muscle and in the SA node. So cardiomyocytes have action potentials that look like this. So basically the potassium 1 channels help set the resting membrane potential of the cardiomyocytes at negative 90 millivolts. And they will have some sort of gradient potential that occurs from the arrhythmic cells. That's the SA node, for example. And this potential gradient is moving through all of the cardiomyocytes, but eventually there is a gradient potential in one. This will activate a transient or T calcium channel, and as well as a voltage-gated sodium channel. And this super quickly depolarizes the cell. And once it gets up towards the peak of this action potential, this one you start to have ITO1 and ITO2 channels open. ITO1 and 2 channels are potassium channels and a calcium activated chloride channel. And this is what's going to quickly hyperpolarize, just for a really short moment, hyperpolarize the cardiomyocyte cell. During this time as well, you have a latent calcium channel that opens. And I believe this is what's going to, help the action potential chart to plateau or level out at the quick instance that it tries to hyperpolarize. During this plateau phase, you're going to have a ultra rapid, and slow potassium channels open. From what I understand, all three channels, they kind of work against each other, but one opens really quickly, one opens somewhat quickly, and the other one opens slowly. The accumulation of all of this will end up helping the action potential of the cardiomyocyte to repolarize back down to its resting membrane at negative 90, actually. And during this time of repolarization, the I calcium 1 channel will be played as well. So then now we have the arrhythmic cells, or what we call the SA node or AV node, even the Purkinje fibers. They're gonna generally look like this. So there is no resting membrane potential for arrhythmic cells, and this is a good thing because we always want the heart to be active, moving always, and the SA node helps stimulate the contraction over and over on a rhythm. This could increase, right, or decrease, as we know, as heart rate can do that. But the lowest point of the action potential chart for a autoarrhythmic cell is at negative 60 millivolts. There's a IF channel that we call. This will always be allowing this gradient potential to help depolarize the cell, if you will, just very slowly until it hits that threshold. And once it hits threshold, then I calcium channel and a voltage-gated calcium channel will allow it to kind of do this dome shape, peak instead of a quick, jagged peak. It is very rounded, and, because those calcium channels will slowly start to close. And then once it starts to repolarize, we have voltage-gated potassium channels and an IK channel for another potassium type channel to allow this to occur, and then it goes back to its rhythm of going back up to depolarize again. So next question is, during each phase of the action potentials, describe the channels, ion currents, and membrane potentials involved. Okay, yeah, so the different phases, so we'll go back to, well, we'll start again with the autoarrhythmic cells. So that initial, repolarization from -60 is phase 4. At this point, our HCN channels, it is a CAMP ligand gated channel to help the flow of sodium. So sodium is like slowly being introduced into the cell until it hits that threshold. The moment it hits threshold, the voltage-gated calcium, T-type, so fast type of calcium, opens, and that quickly helps to repolarize the cell. Sorry, not repolarize, depolarize the cell even more. As that starts to close, because it's a quick type, a L-type calcium channel, so a slower one, is going to just slowly, it's open as well, but it's slowly starting to close, and that's what creates that rounded top of a peak. That helps to slowly depolarize the cell as well. And once it starts to hit the peak where it starts plateauing before it starts going down again, at the top there you have an IK potassium channel, basically. That's going to repolarize the cell back to its -60 resting membrane potential. That will close right at the beginning of phase 4. So that last part is phase 3. And I forgot to mention that phase 0 is right after the threshold is reached. Yeah, and so that, and then the whole thing will happen again where HCN channel will, because due to hyperpolarization, open again. Okay. And then we want to go to the contractile cell. So there's 4, 0, 1, 2, 3, and then 4 again. So right at 4, at the resting membrane potential, the IK1 potassium channels are open. This allows the resting membrane of the cell to be at that -90 millivolts. And so after some sort of potential occurs due to the SA node, sending a gradient towards these contractile cells, depolarization will happen. So it'll start to go up. That is phase 0. In this phase, you have an I sodium channel that opens, and then the original IK1 channel that holds that membrane potential will close. So all we have is sodium channels opening, which sodium rushes into the cell, causing it to depolarize very quickly. Once it goes all the way to the peak, we hit phase 1. That sodium channel will close. At phase 1, the ITO1, which is potassium, and ITO2, which is for chloride, start to open. And this will be rapidly depolarizing the cell just for an instant, a very short phase. Right in that instant, once it's when it opens, it closes, and then it opens up an I calcium type L channel, which is a slow calcium channel. This will open at phase, so this is now going to be phase 2. So this L-type calcium channel, will slowly open, which will create a plateau, so a flat, line on this action potential graph. And then you have all the I potassium channels. You have I ultra rapid potassium, and slow potassium channels all open in that order. And once they all open, so all 3 of them starts to open and allow calcium to rush out of the cell. This is what's going to cause the repolarization, rapid going down back to its resting membrane point, and that is phase 3. So once it hits that resting membrane back at phase 4, or the beginning phase, that latent calcium channel we talked about before that helped the plateau closes. And then same with all the ultra rapid, rapid, and slow potassium channels will also close. And then the whole thing starts over again. Okay, so next we want to talk about ECG tracings and how each of the P, QRS, and T waves are made. So it's a good question. We're gonna go find this picture real quick. So a regular ECG graph will kind of look something like, let's see if I have a picture somewhere. I do not. So you have a electrocardiogram that measures the polarity of the heart in its entirety. A P wave is the first wave we run into. That is the depolarization of the atrium of the hearts from the SA node going towards the AV node. The AV node kind of holds all that, stops the flow of electricity trying to depolarize the heart just for a brief moment. And that in turn will just stop right there for a second, and then it will cause the P wave to kind of just round off and go flat for a second. And then the instance that the AV node allows the electrical gradient to move down and towards the ventricles is going to go through the atrioventricular septum. But in the instant it happens, it is traveling down the left ventricle just a little faster compared to the right ventricle side of that septum. That is due to the left ventricle of the heart being a little bit more thicker in the myocardium. It just has more muscle cells, I guess, and that means the direction of the depolarization of the first part of the septum is kind of going back towards where the atrium was, or I guess, as you say, towards the negative electrode of the lead. And this causes a short but downward spike. And this was going to start the Q of the QRS segment. And then once the whole septum goes through its depolarization phase, it's going towards the positive electrode. And this will create a really big vector going towards the electrode and creates a really big upward R wave. And then following the outline of the heart, after it goes towards the apex of the heart where the positive electrode is, it's going to wrap back up the side of the ventricles and go back towards the negative electrode back at the beginning where the atria is. And that's going to create a quick downward spike in the ECG, and that will create our S wave. So altogether, it is a QRS wave. For brief moments, the whole heart will be depolarized, and because there's no movement of charges or separation of charges, is all one big separation. It's going to be flat for a second. That's going to be our ST kind of interval. And then the heart is going to repolarize starting from the apex, so the very last part, back up towards the atrium. And so this should create a new gradient of electrode separation and charge for positive heading towards a negative, meaning we'll have an upward, stroke on the ECG, and that is going to be RT wave. Okay. So sometimes we have abnormal effects of when we read ECGs in the heart. And so we want to find out what's going to cause these things. So that is primarily for the scope of the class. We're going to talk about NSTEMIs and STEMIs. So an NSTEMI or I guess let's start with STEMI. STEMI stands for a ST elevation myocardial infarction. So basically, our regular ECG tracing that I mentioned, instead of its regular form, we will see that the last two waves that I mentioned, the S and the T, to be elevated higher, and that plateau, those two intervals will actually have a higher, I guess, elevated plateau compared to the baseline of where it starts, right? And that is why we call it a STEMI. It's an ST elevated. And what the cause of that is uh, hypoxia in the either the endocardium cells of the heart, or more typically the whole edge of the heart there. We call it transmural hypoxia. And so because the hypoxia exists due to lack of blood flow, this causes the separation of charges in those cells to not be activated because it doesn't have aerobic ATP to do so. And thus, the direction of their vectors in the heart will create an elevated ST interval, and is what we call a myocardial infarction, or a heart attack, really. And an NSTEMI is what we call a non-ST elevated myocardial infarction, and this is due to in the opposite effect, a depressed ST. I guess it wouldn't be an elevation, it would be a depression of it. So it's actually lower than the baseline of the ECG graph. And this is due to just the endocardium of the heart experiencing hypoxia instead of just the whole wall of that side of the heart. Okay, next we want to move on to describe the mechanisms for the inotropic, lusotropic, and chronotropic actions of norepinephrine and acetylcholine on the heart. So what does this really mean? So really quickly, I'll just say describe what that means. So an inotropic effect is basically a greater increase in contraction of the heart, I believe. Let me double check this real quick. Sorry, it's the opposite. It's a greater relaxation of the heart. So what happens is we have a cardiomyocyte cell, and we have a catecholamine of some sort. So that could be dopamine, epinephrine, or norepinephrine, which is typically epinephrine. This will bind to a beta-1 receptor on these cardiomyocytes. Once it binds to these beta-1 receptors, it is a G protein subunit, alpha subunit specifically, will kind of pop off the G protein, and it'll go to a section of the cell that has adenylyl cyclase. When the alpha subunit gets to adenylyl cyclase, it creates cyclic AMP, or CAMP. It'll increase the amount of that in the cell. When it does this, it's able to create more pKa within the cell. After this point is a cascade effect of the pKa just going to a bunch of different things. It's going to go to a L-type calcium channel, which will increase the amount of calcium that goes into the cell, which will increase the inotropic effect, or relaxation effect. Sorry, I got that wrong. It'll actually increase the contractiveness of the cell. It'll be more likely to contract it, or more frequently contract. This pKa will also go to troponin, which is a type of protein that either once it's activated with calcium, it allows more contraction to happen. But what it does is it's going to inhibit this troponin by offloading calcium that activates it, which will allow relaxation of the cardiomyocyte, and will allow it to or more quickly, I guess, frequently wise, contract the heart again by using the calcium to bind it again. And then the last thing that there's two more. PKA will also inhibit a type of protein that's connected to the sarcoplasmic reticulum. It's called calstabin. This calstabin, once it's inhibited, will open the RYR, or the ryanodine channel, to the SR, or sarcoplasmic reticulum. When this happens, it opens that channel of the RYR and allows more of the SR calcium to enter the intracellular portion of the cell, creating more calcium intracellularly and more of an inotropic effect, allowing contraction to happen. And then lastly, the PKA will then go to where the circopump is of the SR, and that will go specifically to a phospholambin site. This will increase the circopump action, which will reset the cell to have more contraction again. And this is actually a lusotropic action. Lusotropic, I haven't mentioned yet, is actually the opposite of inotropic, and this should relax this cell. So if you have a lot of calcium intracellularly, it's basically more likely to contract the cell. So if the circopump is pumping all the calcium back into the SR, due to lusotropic effects, it'll slowly relax the cell. So, and then I don't think I mentioned this well, but the PKA inhibiting troponin earlier is actually a lusotropic effect. So there's two inotropic, two lusotropic effects. One, for inotropic, it is the PKA going to L-type calcium channels. And it is also PKA going to inhibit calstabin and open RYR channels. And then the other two for lusotropic would be PKA going to the troponin, and then PKA going to the circopump. Okay, sorry, that was kind of long. Okay, we want to talk about, so that was all just for the cardiomyocytes. But we also want to talk about the autorhythmic cells, what's going to happen there. So if epinephrine exists, I just want to add one more thing. Cardiomyocytes is only an adrenergic sympathetic event. There's no parasympathetic events that allows for cardiomyocytes to occur, because they only have beta-1 receptors, which is for adrenergic norepinephrine stuff. But on the other hand, for the cardiomyocyte, we actually have a sympathetic and parasympathetic pathway that allows either or to happen. So we'll just start with the beta-1 receptor that's on the autorhythmic cell. And epinephrine will bind to this. This will allow an alpha subunit to go to adenylocyclase to increase the amount of CAMP, like we mentioned before, same thing, and increase the amount of PKA as well in the cell. This PKA will then have a cascade effect. It's going to open L-type calcium, same as before. And it is also, let me see what else it's going to do. So for autorhythmic cells, when it opens this L-type calcium channel, it's going to decrease the threshold of the action potential of the cell, and it'll increase the slope at phase 0. So what basically this means is that PKA, when epinephrine binds to the beta-1 receptors of autorhythmic cells, it's going to increase the likelihood of this thing to happen more quickly, or otherwise known as an increase in heart rate. Okay, next we want to talk about what happens if acetylcholine, or not adrenergic, but the other one, what is that called? Sorry, so basically acetylcholine, if it hits the autorhythmic cell, is going to bind to an M2 receptor. This M2 receptor is going to release alpha subunits to inhibit adenylyl cyclase, which would decrease what I mentioned just before, decrease in CAMP, decrease pKa, which will then not decrease the threshold, but increase the threshold, and then not increase the slope, but decrease the slope, which will then all turn out to decrease the heart rate of the whole heart, really. Another thing that's actually going to happen is you have a beta and a gamma subunit. They're kind of fused together, so they become one big molecule. And they're going to go towards what we have in the autorhythmic cell that's called a GERK channel. What it's going to do is it's going to allow potassium to exit the cell through that GERK channel. And this effect also decreases the heart rate. Let's see. I forgot to mention in the sympathetic system with epinephrine binding to beta 1 when it increases in CAMP. That CAMP is going to open more of the HCN channels that we have in the autorhythmic cells. When it opens these HCN channels, it'll increase the slope during phase 4. So that slow increase that always occurs for sodium depression is going to increase that more of the slope. And that also increases the heart rate as well. So when we increase the heart rate because of the autorhythmic cells, with a sympathetic pathway using epinephrine and all those things to increase the threshold or increase the slope of this action potentials, is a chronotropic effect. So anytime because of the autorhythmic cells increase in heart rate, that is a chronotropic effect. Okay. Include the mechanism of its release. Explain the role of calcium in cardiac muscle contraction. Include the mechanism of its release into the cytosol and its return into the SR and extracellular fluids. I think I briefly mentioned that already, but so when it's when a catecholamine, for example, epinephrine, binds to a cardiac myocyte cell, it allows more intracellular calcium to exist either by a channel opening so that calcium rushes in the cell, or within the cell, the SR releasing calcium out to contract the muscle of the heart. So I did actually mention that already. We'll move on. Finally, describe the events taking place in the left ventricle and aorta during the cardiac cycle. Okay, so we want to know, the cardiac cycle, what's happening with the heart when it's pumping blood through it. So basically, it's an idea about volume and it's an idea about pressure, really. So blood enters the left atrium, which comes from pulmonary veins. These are freshly oxygenated blood, and once it enters the atrium, it's going to wait till the pressure of the atrium is greater than the pressure of the ventricle, so that blood is going to rush in through there. When this happens, so the blood rushes through the bicuspid valve or atrioventricular valve, it is going to snap back closed because the pressure of the ventricle is now greater than the pressure of the atrium, closing the valve, and it creates a lub sound. So now your ventricular pressure is great, and it needs to start increasing in pressure before it can be sent out of the aorta through the semilunar valve. So typically in a normal heart, the pressure has to of the ventricle has to exceed the pressure of the aorta, which typically likes to stay around 120 on different parts of the cycle. But once the ventricle pressure reaches around 120 is when the semilunar valve opens, allowing blood from the ventricle to rush into the aorta. And so for a second, it'll create some pressure in the aorta. And then it'll slowly close its valve again, right? You don't want that blood rushing back in. In a normal heart, it'll close. For a brief moment, the blood will try to come back, but it's stopped by the valve. But it'll create some more pressure for a minute. And the moment right before it creates that pressure again, we call the dicrotic notch, which is the same moment when the heart or when the semilunar valve closes after the blood goes up and right before it comes back down. This sound of the closing of the semilunar valves is the dub sound that we hear in the heartbeat, so lub dub, also known as the dicrotic notch or S2. Okay, and this happens around a pressure of 80 millimeters of mercury. And I mentioned that 120 millimeters of mercury is the greatest extent of the pressure of the aorta when the blood from the ventricles enter through the semilunar valve into the aorta. Okay, so now the moment that blood rushes back down towards the semilunar valve, it stays closed, but there's pressure like bouncing off the walls of the aorta. The aorta will kind of stretch again. Just momentarily until that blood keeps flowing through either the coronary arteries or down the rest of the system. And then it'll create that cycle again. And this happens very, very quickly, right? Because we want the heart to be on this rhythm of producing blood flow and oxygen through the whole body. So what I talked about was a lot of pressure numbers. We also kind of care about the volume, and so in a let's see, when the blood enters the atrium at the very beginning, we're going to increase it to about 120 milliliters of blood, and this will then, once it hits that threshold, for a moment actually in the in the atrium, it's gonna stay just for a second, and we call it an isovolumetric, which means it's just staying the same volume of blood, basically. But once that pressure that I mentioned earlier increases high enough where it enters the ventricle, then the volume would decrease pretty low until it comes back up due to its ventricles pushing the blood out. One last thing. Sometimes the valves of the heart will be broken in some way or another. We can have issues with the cardiac cycle, and this is typically represented when you hear within the heart a whoosh or a shh sound. And depending on when you hear this sound will kind of help indicate what exactly is wrong with the either the valves or the heart, really. If you hear a lub, whoosh, and then dub sound, that indicates a leaky atrioventricular valve or bicuspid valve, for example. So the blood, when it enters into the ventricle from the atrium, it'll be a little bit leaky and kind of go back out the atrium, and that creates that shh or whoosh sound. But it'll still have a ventricular contraction, sending some of the blood up through the aorta and have the dub sound anyways. If you have a lub and it's kind of quiet, whoosh sound, and then dub. So lub, whoosh, dub sound. that is a semilunar valve stenosis, which I believe means the blood kind of rushes or leaks a little bit through the semilunar valve. But then it gets pushed, all the rest of the blood gets pushed up the semilunar valve anyways, creating the dub sound. And then last but not least, we have a lub, dub, and then whoosh. So whoosh is after the lub sound. That would indicate a leaky semilunar valve. And so the blood gets pushed up from the ventricle into the aorta through the semilunar valve. But due to its broken or leakiness, some of the blood actually goes back into the ventricle of the heart. Okay, that is everything for exam 3 SA1. Thank you for listening. My name is Jacob, and we'll see you again next time.